Alright, let's take a look at this. Question 1, in what way is wave A larger than wave B? So look at wave A and wave B. Well, they have the same wavelength, but A displaces further from equilibrium than B does, therefore it has a higher amplitude. Now, wave A and B both have the same wavelength, and I'm just going to put lambda there because I'm lazy and I don't want to write wavelength. Okay, let's keep going here, and feel free to be lazy yourself in that regard. Let's keep going here. Are waves A and B in phase or out of phase with each other? What you can tell is if they line up crest to crest, they're in phase. If they line up crest to trough, they're out of phase. So these ones here are out of phase with each other. Will they produce constructive or destructive interference? Well, here's what's happening. Wave A, let's just say that these lines here represent meters above equilibrium. Here's equilibrium, 1, 2. Wave A wants to displace the water 3 meters above equilibrium, and wave B wants to drop it 2 meters below. So therefore, they're going to work against each other and produce what we call destructive interference. Now, number 5 wants me to draw the resultant waveform. So what we're going to do here is both A and B start with, you know what, let me get a bigger pin tip here. Alright, let's see how this works. Alright, let's try this again. Alright, oh, there we go. Alright, so now what I'm going to say is if I add positive 3 and negative 2, what I end up getting is positive 1. So I'm going to put a dot here. Sort of, I went a little bit too high. But that's my stylus problem. Now here I got 0 and 0 give me 0. Try to aim better. Now what I find in the next one is I have negative 3 and positive 2, which puts me here at negative 1. And I'm just going to keep going in a similar fashion like that. Now what I'm going to do is I'm going to draw the wave. Oops. I'm going to draw that wave as best I can. And I realize I'm not always hitting the mark, and it's okay if you don't either. But we get the idea. This wave is definitely smaller than either A or B. Now let's move this up. How did the wavelength compare? It turns out the wavelength in this case, let me make my pin smaller. Hang on a second. Alright, let's try that again. Turns out in this case the wavelength was the same. It doesn't change the wavelength. However, the amplitude in this case was smaller. So with destructive interference, the amplitude is going to be smaller. Wow, that went quick. Let's go to the next page. Man, this is easy homework. Alright, are waves C and D in phase or out of phase with each other? They're lining up crest to crest and trough to trough. That makes them in phase with each other. Draw the resultant waveform by combining the values from, okay, so now what we're going to do is I'm going to bring up a better pin tip here. Won't go quite as crazy as I did last time though. Alright, so what we have here is D wants to be 1 meter above equilibrium and C wants to be 2 above it. So when I combine those two, what I get is 3 meters above it. Here they both want to be at 0. Here wave D wants to be 1 meter below and C wants to be 2 meters below, so the combination of the two gives me 3 meters below. So I'm just going to go ahead in a similar form fill in what I get by combining these waves. And now I'm going to go ahead and try to draw that wave. I'm going to get a little bit thicker here though, if you don't mind. Alright, and I'm going to go like this. Up, down, up. And obviously I'm not doing a perfect job, and I don't expect you to either. I just want you to get the sense of the resultant wave is going to be determined in that way. So, basically what we see is we got an increase in amplitude but the same wavelength once again. Let's look at our next one here. Alright, so how does a playground swing illustrate resonance? Well, when a child adds energy to the system in phase or in time with the swing's natural frequency, then the amplitude or the size of the oscillations increases. You don't have to say it quite that way, but that's the basic idea. If you move your legs in time with its natural frequency, it's going to swing further. In other words, its amplitude is going to increase. Alright, the diagram above, put an N. We have a standing wave. We're going to put an N at each node and an A at each antinode. Let me go to a smaller pin tip here. That should work. Alright, so here I have a node. Here I have a node. Here I have a node, and here I have a node. Nodes are points in a standing wave that stay at equilibrium. And then antinodes are the points halfway in between where you get maximum displacement. So here's an antinode, here is an antinode, and here is an antinode. Which harmonic is shown? Well, to find the harmonics, if you want to know the harmonic, all you do is count the antinodes. I have one antinode, two antinodes, three antinodes. This must be the third harmonic. And finally, if the standing wave shown has a frequency of 600 Hertz, what is the frequency of the first harmonic? Well, the thing to keep in mind is this, that each harmonic is a multiple of the first harmonic. So, for instance, the second harmonic is 2 times the first harmonic, the third is 3 times the first, the 12th is 12 times the first. So this one is the third harmonic. So if it's 600, 600 equals 3 times the first harmonic. So in other words, this is 3 times bigger than the first harmonic. What number is 3 times bigger than 600? The answer is going to be 200. And there's your homework. Hope it went well for you. Hey, school year's almost over. Take heart.